Let's solve an interesting problem in kinematics. Point A moves uniformly with velocity v so that the vector v is continually aimed at point B, which in its turn moves rectilinearly and uniformly with velocity u, where u is less than v. At the initial moment of time, the velocity vectors v and u are perpendicular to each other, and the points are separated by a distance L. How soon will the points converge? Let's visualize this problem first. We have 2 points, A and B. B moves in a straight line with constant velocity u. A moves with velocity v, which is always pointed directly at B. Initially, we're told that the velocity vectors are perpendicular, and the points are at a distance L apart. Now, let's animate the motion to better understand what's happening. Point B moves in a straight line with velocity u. Meanwhile, point A constantly adjusts its direction to always move directly toward B's current position. Since v is greater than u, A will eventually catch B. What makes this problem interesting is that A doesn't follow a straight path. Instead, it follows a curved path as it continuously aims at B. Let's now think about how to determine exactly when they'll meet. To solve this problem analytically, let's set up a coordinate system and analyze the initial conditions. Initially, we'll place B at the origin, and A at a distance L directly below. B moves horizontally with velocity u, and A initially moves vertically with velocity v. At any moment, the key insight is to look at the closing speed between these 2 points. Since A's velocity is always aimed at B, the component of A's velocity along the line connecting A and B is always exactly v. Meanwhile, B's velocity has a component along this line that changes over time as the geometry changes. The effective closing speed between the points is therefore the difference between these components. Now, let's derive the closing speed mathematically. To solve the problem, we need to analyze the triangle formed by A, B, and the point where their velocities are perpendicular. Using trigonometric relationships, we can show that when v is always aimed at B, the closing speed remains constant at v close equals the square root of v squared minus u squared. Since the initial separation is L, the time to convergence is t equals L divided by the square root of v squared minus u squared. This elegant result tells us that despite the complex path that point A follows, the time to convergence depends simply on the initial separation and the difference between the squares of the 2 speeds. In conclusion, we've solved a classic pursuit problem where one point always aims at another moving point, and we need to find when they'll meet. The key insight is that even though point A follows a curved path, the closing speed remains constant at the square root of v squared minus u squared. Therefore, the time to convergence is L divided by this closing speed, giving us our final answer, t equals L divided by the square root of v squared minus u squared. This elegant result demonstrates how seemingly complex motion problems can be solved with careful analysis of the relative motion between objects.